Welcome. Today we're going to move from the concept of information bottlenecks to the concept of focus. We are going to deconstruct one of the important breakthroughs in deep learning, the attention mechanism. While many of you know the basic of sequence-to-sequence models, today we will see exactly why they failed at scale and how attention fixed them, paving the way for the transformers that we use today in ChatGPT, Gemini, DeepSeek, all of the modern large language models. So let's briefly recap the standard machine translation framework, the Encoder-Decoder. In this setup, we have an encoder that reads the source sentence like English, and a decoder that generates the target sentence like Spanish. The encoder processes the input sequence, and the decoder maximize the probability to the of the correct target sequence based on what the encoder had. But here lies a problem in the context vector. In a traditional RNN or an LSTM, the encoder reads the input token by token. So at the very end, it produces a single final hidden state, often called the context vector. This vector is supposed to capture the entire meaning of the input sentence, whether the input is 3 words, 300 words. The model is forced to compress all that information into one fixed length vector. So this compression creates an information bottleneck. Like imagine describing the entire universe in a single vector. You're going to lose details. Consider this example. I got this example from a video on StatQuest. It's don't eat the delicious looking and smelling pizza. If the sentence is long, the encoder might forget the word don't by the time it reaches pizza. So if that first word is lost in the bottleneck, imagine we don't have this word. So eat the delicious looking and smelling pizza. The meaning flips entirely and the translation becomes eat the pizza. We need a way to stop forgetting. So now we come to the solution. The solution proposed is simple but revolutionary. Stop trying to squeeze everything into one vector. Instead, let's create a path from every single step of the encoder directly to the decoder. This allows the decoder to search through the entire source sentence effectively at every single step of generation, rather than relying on just the final memory. So you don't memorize the whole book and then write the translation from memory. You read the sentence as you write the translation. You read a sentence as you write the translation. You look back for the specific source words that correspond to what you're currently writing. Attention allows the neural network to perform this soft search for relevant parts of the source sentence. But how does the model know where to look? At every step, the model asks, how relevant is the specific input word to the word I'm trying to generate right now? We calculate a similarity score between the current decoder state and every single encoder state. There are different ways to calculate this, but the common one is the cosine similarity. or dot product, but the goal is to measure how much the current output aligns with a specific input. These raw scores can be any number. To make them usable, we pass them through a softmax function. This converts the scores into probabilities that add up to 1. For example, the model can say 60% focused on the word go and 40% focus on the word let's. We then calculate a weighted sum of the encoder state based on these percentages. This creates a custom context vector unique to this exact millisecond of generation. So for every word we have a different context vector that is a weighted average based on these percentages. This is the beauty of attention. It is interpretable. We can visualize those weights in a matrix. Here the x-axis is the source sentence, the y is the generated translation. The white pixels represent the high attention weights. This shows us exactly which source word the model was looking at when it generated that specific target word. Let's look at a specific example. Let's see. In English, we say European Economic Area. In French, the order is Zone Économique Européenne. The adjectives and nouns, like they're reversed or swapped the places. The attention mechanism handles this naturally. We can see the focus points like jump over words and look back. Like, let's use another color. Jumped over some words and look back to align the adjective correctly, effectively solving the word ordering problem without complex manual rules. So, and here this is what we call soft alignment. In a hard alignment, one word translates to one word, but consider translating the man to the French Blom. To choose the L instead of the, because in French there is L, le, and la. In English these three are can be represented by the. So the model needs to know the next word, because this one is based on the feminine words, masculine words, and this is if the next word starts with a vowel. So they depend on the next word. So the model needs to know the next word is homme or man, which is masculine, and starts with a vowel. Soft alignment allows the model to attend both the and man simultaneously to make the correct grammatical decision. Now let's evolve like the concept. In standard embeddings like word2vec, the word mole has one fixed vector, but mole can mean like spy, this animal, the skin blemish. Without context, the embedding is ambiguous, so we need to wait for the word mole to look at its neighbors in a sentence to figure out which version of itself it should be. This brings us to self-attention, the engine of transformer. In sequence to sequence, the decoder look at the encoder. In self-attention, words within the same sentence look at each other. For example, in the phrase blue and soft creature, the word creature can attend to the blue and soft to update its own meaning from a generic thing to a colorful, fluffy thing. So it looks at the adjectives. So to implement this, we use the golden analogy of attention: query, key, and value. Like, imagine this filing system. Query is what am I looking for? For example, am I an adjective looking for a noun? The key is what defines me. I am a noun. The value is what information do I hold, like what my meaning. If the query matches the key, we extract the value. Through this mechanism, embeddings become contextual. Take the word tower, for example. If tower attends to the word Eiffel, next to it the vector updates to word Paris. And structure. If it attends to the word miniature, its vector updates away from large towards toy. Attention actually changes what the word means based on what is around it or its neighbors. So why one head isn't enough? The head is a focus point. One focus point isn't enough because words play multiple roles. For example, the animal didn't cross the street because it was too tired. What does it refer to? To the street or to the animal? If we use a single attention mechanism, we might focus only on the grammar, but we also need to track who the subject is, the tone, and the position. So we use multi-head attention. We run the attention process multiple times in parallel. For example, GPT-3 uses 96 heads. One head might track subject-verb agreement, another track the next word neighbors, another might look for rare words. This gives the model a rich, multidimensional understanding of the text. So why did attention take over the word? It solved the bottleneck. No more squashing like long sequences into one vector. It is interpretable. We can see exactly what the model is thinking. Also, it is parallelizable, unlike RNNs, which must run one word at a time. Attention can process the whole sentence at once on a GPU, so it's way faster. We now have the intuition. We compare queries and keys to get values. In the next presentation, we will peel back like the layers and look at the math, the dot product, the matrices, and the scaling factors that make this theory a mathematical reality. So thank you for watching.